Here's a video explanation of a problem, a word problem from the rational functions section when we need to have a right circular cylinder, a cylinder that has a volume of 40 cubic inches, and we have a cost for the top and bottom have to be stronger, so they cost more. And in this case, they cost 4 cents per square inch, while the sides only cost 1 cent per square inch. And we want to build a cylinder that's big enough to hold 40 cubic inches, but has the smallest possible cost. We want to minimize the cost in this example. And we talked about this in class, but I never did a full explanation. So let's try that. So first you need a formula for the volume, and the volume is pi x squared times h. That's the base. That's the base times the height. The area of the base times the height, that'll give you the volume, and that is supposed to be 40 cubic inches. Great. So how do you find the cost? The cost of the metal in terms of the radius in this case would be, let's see. So here's the top and the bottom. It's 4 cents per square inch times the area in square inches of the top and the bottom added together. And so that is going to be 2 times pi x squared. The area of the bottom is a circle. The area of that is pi times the radius squared. Double that for the top and bottom, and then multiply by 4 cents per square inch. What about the cost of the sides? The cost of the sides is, we have to find the area of the sides. And if you think about a cylinder, the distance around it is 2 pi x. And if you open that up, it becomes a rectangle, like this rectangle I've drawn here. And the length of that rectangle is going to be the circumference of the circle, which is 2 pi x. And the height of the rectangle is the height of the cylinder, which is h. So we get a formula for the cost in terms of the radius and the height. But we want it in terms of just the radius. So we need to replace the height with an expression in terms of the radius. And so the key is they're connected by the volume formula. So we can use this formula, 40 equals the volume, pi times the radius squared times h, divide by pi radius squared to get h on its own, and take that and replace the h in our cost formula with that formula for h. And that's where we start getting a variable in the denominator. That's why it's going to be a rational function. We get an x squared in the denominator. And when you simplify that, so multiply everything out, the first half becomes 8 pi x squared. The second half, the pi's cancel out, and the 40 and the 2 become 80. One of the x's cancels one of the x's in the bottom. So we have a nice rational function, and the way we have talked about this in the class is we don't know how to graph these, or we can graph them, but we can't find the y values for the bottoms of the curves, which is what we're trying to find, without a calculator. So I wanted you to just do that. So I simplified it. I combined it into a single fraction, and we're going to have a vertical asymptote at 0, and otherwise it's going to have the end behavior like x squared, well, 8 pi x squared. It'll go up on both sides. And I graphed this on Desmos, and it looks something like this. There's a vertical asymptote at 0, and the key point I'm looking for is that one right there. Because this part of the graph over here is irrelevant for our problem because that's the radius being negative, and that can't really happen in reality. So what we're looking for is that minimum value there. And if you zoom in on it in Desmos or on your calculator, I found that it was 1.158 inches. And that's the radius. And so then what's the height? Well, you can plug that 1.158 back into the height expression, and after a little bit of trial and error, I got that it was 9.5 inches. So when you solve this, you're going to get a cylinder, but it's a really skinny, tall cylinder because the top and bottom are expensive. So you kind of want those to be smaller, and the sides are cheaper, so they can be long and tall. But you still have to have it big enough so that it has the total volume of 40. So there's a problem on the midterm that is similar to that. And if you can set up a cost function like this, where you have the cost of the top and the cost of the sides, and see that, then plug that into a formula, graph the formula on Desmos or on a graphing calculator or something and find a minimum value. That will minimize the cost. Hope that helps. Bye.